Hello, this lecture will cover pages 260 through 264 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on digital arithmetic 6C, in specific, arithmetic overflow. We're on page 260, and we're going to talk about something that you're going to run into in the future, and they want us to present it in this digital class. It's referred to as overflow, and its symbol was with a V. There are 3 rules to remember regarding overflow. Before I show you these 3 rules, I want to make it real clear that overflow and carry are 2 different things. It's pretty easy to understand what a carry is. We've been using the carry bit. Some instructors will define as the overflow is a carry into the sign position bit. But I'm not even going to go there. I don't want you to have any association between carry and overflow. Let's talk about overflow. There are 3 rules to remember when regarding overflow. Rule number 1, the addition of 2 numbers with opposite signs, the overflow can never occur. You can never get an overflow condition when you're adding 2 numbers with opposing signs. Why? Here's a Cartesian coordinate plane, because you have a negative number and you're adding it to a positive number, and the result is getting closer together. You're not out at the extremes here. Just remember that. You'll never get an overflow if the 2 numbers have opposite signs. Rule number 2, addition of 2 numbers with the same sign. Overflow occurs whenever the sign of the result is opposite the sign of the 2 operands. No, this is going to explain that, but once I explain it, I want you to read this again. It's pretty easy to understand. Here we have an 8-bit number, A7 through A0. Here we have an 8-bit number, B7 through B0. This is the sign bit. A7 is the sign bit for the A number, and B7 is the sign bit for the B number. If you have a positive number and a positive number, these are both 0. If the result is 0, it's telling you have a positive number, you're adding it to a positive number, and you got a positive number, which is nothing's wrong with that. If you have a negative number, if there's a 1 there, forget about what negative number it is. If there's a 1 there and a 1 there, and you get a 1 there, then you're adding a negative number, you get a negative number. If there's a 0 there, like we just said, and there's a 0 there, and you get a 0 there, you can't have an overflow. But if you have a positive number here and a positive number here, and you get a negative number here, in other words, you have a 0 here and a 0 here, when you add all these up, you're getting, oh, here I go, you get a carry from this bit into this bit, and this becomes a 1. How can you take a positive number and add it to a positive number and get a negative number? You can't. That's an overflow condition. Here it is. If this is low, and this is low, that can't be high. That's what I just explained to you here. That's an overflow condition. Or, what about if this is 1 and this is 1 and you get a 0? How can you take a negative number and add it to a negative number and get a positive number? That can't happen. If that's a 1 and that's a 1, and this becomes a 0, that's an overflow. So you get an overflow condition in either of these 2 cases. No, you can see, you can see why some instructors would refer to it as a carry into the sign bit, because that's how you get this sign changing down here. But that's called an overflow. It's not called a carry. Look over Rule 2. Rule 2 explains how you get an overflow condition, and there it is. There's the Boolean expression for it. I just explained it twice here. Rule number 3. Always ignore the overflow bit when you're using unsigned math, because it has no meaning. Whoops. That's rule 3. Always ignore the overflow bit using unsigned math because it has no meaning. If you think about that, you'll understand it. And we're going to do many examples here. But you saw something similar to this. Let me give you a rule for 2's complement math when it comes to the carry. You always ignore the carry bit when you're using signed math because it has no meaning. Let me read that again. Remember I told you, you always ignore the carry bit when you're using 2's complement math because it has no meaning. Conversely, you always ignore the overflow bit when you're using unsigned math because it has no meaning. Think about 2 unsigned numbers. 2 unsigned numbers, you don't worry about overflow. There isn't going to be an overflow. It's unsigned numbers. So here's an example that you're going to have for homework, and you're going to have on a quiz, and you're going to have on the final. Matter of fact, I'll give you 4 examples right here. So it must tell you this is pretty important. So look them over. Number 1 is a 6 Baker, and number 2 is a 2 Charlie. There's 2 parts to this problem. I want you to add these 2 numbers up, treat them as unsigned numbers. In other words, these are unsigned numbers, and treat them that way. And I want you to give me the state of the carry flag and the overflow flag, or the carry bit or the overflow bit. We'll call that for now. And then interpret the meaning. And then you're going to do the same thing. You're going to take the 2 numbers and you're going to interpret them as signed 2's complement numbers. You're going to do the math, and then you're going to interpret the carry flag or the carry bit and the overflow bit. We're going to do a couple together. Let's start out. Here is your 6 Baker. Here's your 6 Baker. Here's your 2 Charlie. Here's your 2 Charlie. And all the microprocessor is going to do is add them up. Just going to add them up. Matter of fact, the microprocessor does the same thing. What I do up here is the same thing I'm doing out here. It just adds them up. So you add these up, and this is the result. I want you to take a look at the result here. And incidentally, I did the decimal math out here so you can see what it's doing. I think maybe you'll be able to relate the carry and the overflow flags if you take a look at the decimal math. Some students get to associate that a little better. But let's take a look. What's the carry flag do? The carry flag, that carry bit, there's a register, there's a flip-flop. You're going to see this in your homework. There's a flip-flop that just gets set or cleared, and we call the output of that flip-flop a carry bit or a carry flag and the overflow flag. And then the programmer is going to act on this. But what does the hardware do? Well, the carry is equal to 0. There it is. The carry is cleared. And the overflow, what's the overflow? Do you get a 1 or a 0 for overflow? The overflow is equal to a 1. Why? Because that's a 1? No. Too many students miss this on the final. If this is a 0, the carry's a 0. If this is a 1, the carry's a 1. But the overflow don't work that way. That overflow flag gets set to a 1. You have an overflow condition. Why? Because the processor doesn't know these are unsigned numbers. It's a 2's complement processor. Microprocessor chip. Controller. It thinks that's a positive number, and you're adding it to a positive number, and you're getting a negative number, so it just sets the overflow flag. That was that rule 2. That's an overflow condition. Now you have to interpret them for unsigned math. The carry being equal to 0 means the number's good. You don't have to go to double precision. You didn't get a carry to the 9th bit having you put another byte out here. So the number's good. What's the overflow mean? You ignore it. Why? Because you always ignore the overflow bit, whether it's set or cleared, when you're using unsigned math, because it has no meaning, and you're working an unsigned problem. Let's get down here and look at part B to this problem. In part B to this problem, it says same thing. You're going to add the 2 numbers up, and you're going to treat them as signed 2's complement numbers. So you come down here and you add the numbers up, and I should put a plus there because we're working with signed numbers now. This is done exactly the same way by the processor. And the carry flags, those carry flip-flops, are set the same way based on the conditions because it's a 2's complement processor. So the math is done the same way. The carry flag is equal to 0, and the overflow flag, for the same reason I explained up here, got set to a 1. Now interpret the meaning. You're the programmer that has to act on these. We're going to interpret the meaning, signed math. Carry equals 0. I don't care whether carry is equal to 0 or carry is equal to 1. You always ignore it. It's not applicable when you're working with 2's complement math. And the overflow flag being set to a 1, the number's no good. It's too large to fit in single precision, so you need to go to double precision. That's what that's telling you when you're working with signed 2's complement math. There we did one example. Here's example number, I call this example number 1. Say we have two 8-bit signed binary numbers that are added to produce. Now, the mathematics is all done the same way, so I'm not going to go through this again. I'm just going to tell you here in these examples, you get, this is assigned binary numbers, and carry goes to a 1 and overflow goes to a 0, and I want you to interpret their meaning. On the exam, you're going to have to actually do the math and tell me what the carry and what the overflow, whether the carry gets set to a 1 or a 0, or whether the overflow gets set to a 1 or a 0, and then you're going to have to interpret it. But keep in mind here, I'll say it one more time, you can always just, whatever you get out here, if it's a 0, the carry's a 0. If it's a 1, you get a 1 here. The overflow, you have to go back to those rules. If these are ever different, you can never get an overflow. You don't take this bit, if it's a 0, and put a 0 there, and if it's a 1, you put a 1 there. It don't work that way. You have to look at the rules. And no matter how many times I'll explain this in my face-to-face class, the students miss 15 points on the final because of it. This says there's a positive number, and there's a positive number, and you get a negative number. Forget about it being unsigned. The processor doesn't know that. It's a 2's complement machine. The hardware's already making decisions for you. You have to interpret them. So you put a 1 here, not because there's a 1 there, because of rule 2. If these are ever different, I don't care if that's a 1 or a 0. That's going to be a 0. Because you can never get an overflow condition when these are different. So back to these examples right here now. Example number 1, say we have two 8-bit signed binary numbers that are added and produce carry equal 1 and overflow equals 0. Interpret the meanings. It's signed binary numbers. When I say signed binary, 99.9% of the time, I mean 2's complement. And so will everybody else. Here's your answers. Make sure you understand that. Example 2. Say we have two 8-bit unsigned binary numbers that add and produce a carry equal to 1 and an overflow equal to 1. Interpret their meanings. Here's the answer. On page 263, say we have two 8-bit signed binary numbers that add and produce a carry equals 0 and an overflow equal to 1. Interpret their meanings based on signed binary numbers. I've done that for you. Here's the answers. And here's example 4. This is so important, I gave you a separate homework assignment on it. So page 264. There's page 264 is a separate homework assignment. Problem 1 and problem 2. What you have to do, these are formatted exactly the way you're going to be answered. You're going to have to work the problem out on quizzes in the final. You're going to have to provide the answers in hexadecimal form and specify the state of the carry and overflow and negative flags and interpret their meaning. A and B for part 1. Here's the two numbers. And here's problem 2. Same thing. Provide the answers in hexadecimal form, just as an abbreviation, and specify the state of the carry flag, the overflow flag, and the negative flag, and interpret their meanings. This is pretty much the way that we did this problem here back on page number 261. The only difference is I'm giving you different numbers here in both problems. So you might want to look over page 261, but that's important. And that concludes this lecture.